Welcome back. In the previous lecture, we solved the Schrödinger equation for a qubit. In this lecture, we deal with the Heisenberg equation for the same situation. We also learn a lesson about the time dependence of the Hamilton operator and that of the statistical operator. So we have this two-level system, excited state, ground state, with an energy difference of h bar omega. We assign energy 0 to the ground state, energy h bar omega to the excited state. Then this is the Hamilton operator, has value h bar omega in the excited state, value 0 in the ground state. And for the wave function, which is the probability made up of the probability amplitudes for the ground state and the excited state, we find this time dependence. It's the original wave function at time 0 times this matrix, which simply multiplies the components with 1, no change at all, and a phase factor for the excited state. Now it's a two-level system, so we should be able to use the machinery that we have developed for two-level systems, two-state systems, qubits, whatever is the terminology that you prefer. So we will now look at what are the operators here that will play the role of the qubit operators x, y, and z. Or, if we use the Pauli notation, sigma x, sigma y, and sigma z. So, since our wave functions are made of components for the ground state and the excited state, the natural choice for z is the ground state, ket bra minus the excited state, ket bra. Because then z is represented by a matrix which is 1, 0, 0, negative 1, and that just goes nicely with this kind of choice for the wave functions. So let's stick to this. However, things depend on time. So we should really write z of t is the gt ket bra minus the excited state ket bra, but now emphasizing that these kets and bras all depend on time, and so the operator depends on time. And we have already found out how the bras depend on time, because this is essentially what this equation says. Now what about x and y? Well, x is gt et plus et gt. So this would correspond to the matrix 0, 1, 1, 0, as always. For the y operator, we have the matrix 0, negative I, 0. And so the I will go with excited state, ground state, ket bra, and the negative I will go with ground state, excited state, ket bra. Because the top row and the left columns refer to the ground state, and the bottom row and the right column refer to the excited state. So we have these operators. Now what about the Hamilton operator? What does the Hamilton operator look like here? Well, we have to remember that there is also the identity, and the identity is just ground state, ket bra, plus excited state, ket bra. So it's just the completeness relation for these two states, but it's a completeness relation for the states at time t. Whatever is the time t, this ket bra for the ground state and the ket bra for the excited state add up to the identity. So this is true for all times t. And so how do we get the ket bra for the excited state with itself? Well, it's a piece here and it's a piece here. And clearly if I take 1 minus z of t, I will get the excited state ket bra twice. I have the identity with the GG ket bra. I'm subtracting the GG ket bra. There's a minus sign here. I have the excited state ket bra in the identity, and now I'm subtracting negative excited state ket bra. So I'm adding it, and so I end up with a factor of 2, which is to say that this Hamilton operator in this language is equal to h bar omega half 1 minus z of t. So let's see then what Heisenberg's equation of motion says about this situation. Okay, we begin with the time derivative of z of t. Now, the z of t has eigenvalues that do not depend on time. We just saw it's the GG ket bra minus the EE ket bra, but the numbers that appear here are the numbers that appear are plus 1 and minus 1. They do not depend on time. So there is no parametric time dependence, and the whole time dependence comes from the dynamics. So it's the commutator of z at time t with the Hamilton operator that refers to time t, which is z of t itself, essentially. So there's a z of t here. The Hamilton operator is just a simple constant, the identity, and z of t. So it doesn't matter in which order I multiply, and I just get 0. What about x? X of t, well, it's the same story, no parametric time dependence. So now I have the commutator of x and t and the Hamilton operator at time t. Now we have to work this out, because it's x of t here, but z of t there. First of all, the commutator of x with this constant, h bar omega half times 1, that commutator by itself is 0. So we don't have to worry about this constant. But there is the minus z of t. So let's just be systematic about this. It's h bar omega half, and then with a minus sign, and then the commutator of x at time t and z at time t. What's the commutator? The commutator is the product in one order minus the product in the other order. But we know from the earlier lectures that the product of x with z is negative I times y, and the product of z and x is positive I times y. So together we have negative 2i y of t. So this time derivative of x is 1 over I h bar minus h bar omega half, and then negative 2i y at time t from the commutator. So cleaning up, minus signs cancel, 2i here cancel, h bar cancels. All that is left is omega and y t. Now we look at the time derivative of y of t, and that's the same procedure, only that it's now y of t and the Hamilton operator. Again, we have 1 over I h bar, we have negative I omega half, and then we have y of t and z of t. And here we have to deal with the commutator of y and z. We recall again that the commutator is the product in one order minus the product in the reversed order. Now y times z is I times x, and z times y is negative I times x. So we get 2i times x, and so similar to here, except that it's plus 2i rather than minus 2i. So we end up with minus omega x of t. And we continue with that. So here are the Heisenberg equations of motions that we just found. For z of t is very simple, no time dependent. So z of t is just equal to z of 0. The z operator at one time is equal to the z operator at another time. What about x and y? Well, the time derivative of x is really given by y. The time derivative of y is given by x. And so this is a coupled system of equations, actually quite a familiar coupled system of equations that one meets in many different contexts in physics. So there are standard ways of solving them. One of the procedures, the one that I will use now, is to look at not the time derivative of x and y, but at the time derivative of x plus iy. So what's that? Okay, the time derivative of x is omega y. The time derivative of y is minus omega x. So we have minus I omega x of t. I'm cleaning this up and I get minus I omega x of t. And for the omega y, it will be plus I y of t, because the negative I times the positive I is the plus 1 that we have here. So this derivative of this combination, the time derivative of this combination, is actually exactly the same equations of motion that we have seen before for the Schrödinger equation for the bra for E of t or the second component of the wave function. So this is solved by x of t plus I y of t equals e to the minus I omega t x at 0 plus I y of 0. And now we can take the adjoint of this equation, which would be x of t minus I y of t, because the x and the y are their own adjoints. And here we get the complex conjugate of this factor, and here we get the adjoint of this operator. And so now we can extract the x of t by taking half the sum of these equations. So x of t is half the sum of this left-hand side, so it's equal to half the sum of the right-hand side. So let me just go through this slowly. It's for the x of 0, it's half of e to the minus I omega t plus e to the I omega t x of 0. And for the y, it is half of I e to the minus I omega t minus I e to the I omega t y of 0. And so if we now remember that this is the cosine of omega t, and this is the sine of omega t, and we have found x at time t expressed in terms of x at time 0 and y at time 0. Just like here we have z at time t in terms of the z at the early time, here we have x at any time t in terms of x and y at the initial time 0. Right, so we have z of t is just equal z of 0, x of t is the cosine omega t times x of 0, sine omega t times y of 0. And now from the expressions that we just erased, we can also get y of t by taking imaginary parts or differences of x plus I y of t and x minus I y of t. But it's simpler to go back to these equations and notice that I get y of t by just differentiating x with respect to t and dividing by omega. And when I do that, I differentiate the sine omega t. That will give me omega times the cosine omega t. Divide by omega, it's cosine omega t. And then there is y of 0. And then we differentiate the sine omega t. Well, that will give us negative omega. Differentiate the cosine omega t. That will give us negative omega the sine omega t. Omega is cancelled, but the minus sign we have to keep track of. And so this is just like that. So if we now look at these three time-dependent operators together and remember that they make up a vector, the Pauli vector, which has the components x of t, y of t, z of t. So this is the components of this vector as it refers to a particular coordinate system that, for directions x, y, and z. Then what do we have here? Well, again, we have a matrix multiplying what this vector is at time 0. And for z of t, it's easy. There is just a 1 here, and the z doesn't appear in the other solution, so we have zeros here. And for the x and y, we have the cosine omega t, sine omega t, negative sine omega t, cosine omega t. So this matrix describes a rotation of sigma around the third axis, the z-axis. So the dynamics of this sort of system is very simple. We have a Hamilton operator that involves the z operator only, and as a result, the time dependence of the full Pauli vector operator with components x, y, and z is just a rotation of the vector around the z-axis. So now we will see how all of these things go together and are consistent. So still talking about this system with two states, excited state, ground state, with an energy separation of h bar omega. And I mentioned earlier that omega is a circular frequency. Well, we now understand why that is good terminology. Because if I look at these expressions for the time dependence of the operators x, y, and z, or the time dependence of the wave functions, the essential ingredient is the cosine of omega t, the sine of omega t, or their combination in e to the minus I omega t, where we have the cosine of omega t minus I times the sine of omega t. Now, how long does it take for the system to go back to where it started? Well, you just need that the e to the I omega t is equal to 1, and that happens when omega t is equal to 2 pi, and that happens at time t equals 2 pi divided by omega, and there you have it. If you have a frequency nu, then you have a circular frequency of omega equals 2 pi nu, and so this is then 1 over nu, and so the period of this oscillation that we see here, cosine and sine are the basic oscillatory function, is just given by 1 divided by the frequency, as it should be. So this has is oscillatory motion with a period capital T 2 pi divided by omega, which is 1 over the frequency for frequency nu. So it is actually quite common to talk about this and not make a big distinction between circular frequency and frequency. So physicists will often talk about omega as the frequency, but technically speaking, it's the circular frequency. So it differs from the actual frequency by a factor of 2 pi. So that's one observation. The other observation is that if you look here, we have the Hamilton operator. We have indicated that it's the Hamilton operator for time t, because the expected state ket and the expected state bra, they both depend on t, because all kets and all bras depend on t. But in this particular situation, after we solve the equations of motion, we find that the z of t is equal to the z of 0. So the Hamilton operator at time t is the same as the Hamilton operator at time 0. So in this particular situation, the Hamilton operator does not depend on time. Now, how does this square with Heisenberg's equation of motion that things should depend on time? Well, if we look at this Hamilton operator that we have here, it has no parametric time dependence. So there is no term of this kind. So in the general Heisenberg equation of motion, we have these two terms, 1 over IH bar, and then there is the operator and the Hamilton operator. Now the commutator of the Hamilton operator with itself, that is always 0. So it is always true that the total time derivative of the Hamilton operator is equal to the parametric time dependence. But here, this is 0. We have no parametric time dependence in the Hamilton operator, and therefore the Hamilton operator itself does not depend on time. What we call energy is not a time-dependent concept in this setting. So this is sort of as expected because we assigned the same energy to the excited state and the ground state for all times. We always have energy h bar omega for the excited state and energy 0 for the ground state, so the energy does not depend on time, so the Hamilton operator should not depend on time, and it doesn't. Okay, so and now let's move on and talk about the time dependence of the statistical operator. So we assign energy h bar omega to the excited state, energy 0 to the ground state, with no reference to time. The operator that describes the energy, Hamilton operator, therefore will not be dependent on time, and it doesn't. Total time derivative of the Hamilton operator is 0, no time dependence. Now let's turn our attention to the wave functions and the kits and the brass. So what this says is that the GT ET column of brass is equal to 1, 0, 0 e to the minus I omega t times the column of brass at time 0. Why is that? Well, because the state kit that appears here also appears in the psi 0, so we can just sort of mentally remove that from the equation, and then we have an equation about the time dependence of the brass. After all, this is where it comes from. It comes from the time dependence of the brass and the Schrödinger equation for it. Now, there's a corresponding equation for the kits, which we get by just taking the adjoint. So we have the kit for the ground state, the kit for the excited state. Together they are a row of those kits. And so we take the adjoint of this, we get the row of these kits at 0, and the adjoint of this matrix. Of course, we would also find this statement by solving the Schrödinger equation for the kits. We solved it for the brass, but the Schrödinger equation for the kits is just the adjoint, so the solution is also the adjoint. So now let's look at the state kit. Well, the state kit is the basis of kits g of t, e of t, times the wave function at that time, g of t, e of t, where of course we just see the g of t ket bra plus the E of G, E of T ket bra, multiplying the state bra, and so it's the identity, the completeness relation for the states at time t once more, and so it borders on a banality to say that the state ket is equal to the state ket, but if we insert these states, then we have the basis of kets at time t and the wave function that goes at time t. And so now let's see what is the time dependence that we would expect for the statistical operator. Here is yet another way of looking at the same thing. The state ket is the basis at time t times the wave function at time t. The wave function is made up of these two components, probability amplitude for the ground state, probability amplitude for the excited, as it goes with those kets that we have in the basis. Now, if we relate everything to time 0, then this is the G ket at time 0 and the E ket at time 0, and then the matrix that we just saw, 0, 0, e to the I omega t. And for the wave function, we have this matrix, 1, 0, 0, e to the minus I omega t. And then we have the wave function at time 0. And so the time dependence of the kets is from this factor, the time dependence of the wave function is from this factor. But the product of these two matrices, that's just the 2 by 2 identity matrix. So we end up with the basis at 0, the wave function at 0, equal to the basis at time t, the wave function at time t, which is just saying that this combination of basis at time t times the wave function at time t, this product does not really depend on time. It's the same operator, the same ket that we get from this combination, independent of which time we talk about. The basis at time t, the wave function at time t, we combine them to get the state ket. The state ket itself does not depend on time. It shouldn't depend on time because the state ket summarizes what we know about the preparation of the system, and this preparation, by its nature, refers to an initial time when the state was prepared. So the state is prepared with particular amplitudes for excited state and ground state, and that's the information that we have about the state. Now, if we talk about corresponding amplitudes at later times, well, then we have other numbers for that, but these other numbers also refer to other basis kets. So it's fine that we have a time-dependent wave function. We usually get this from solving the Schrödinger equation, but we must remember that this time-dependent wave function also refers to a basis which has changed in time. And if we take all these time dependencies together, we end up with something which does not depend on time at all. So the statistical operator for a system like this, we write the letter rho as usual. Well, that's just the ket bra made from the state ket. Now we know that these kets and bras do not depend on time, so the statistical operator does not depend on time. I take the time derivative, and that's just 0. But isn't it true that for all operators we have Heisenberg's equation of motion? Yes, that's true. And in this case, it says that 0 is equal to the parametric time dependence of rho plus the dynamic time dependence. So I remind you, this is the parametric derivative, and this is the dynamic derivative. So it's a parametric time dependence, a dynamic time dependence. How do we see this? Well, the statistical operator for such a two-level system, such a qubit as we know, is half the identity plus the Bloch vector times the Pauli vector operator. Now these are quantities that depend on time. And so if there is no total time dependence, then the time dependence of the Pauli vector and the time dependence of the Bloch vector and the time dependence of the Pauli vector operator, they have to compensate for each other. Now we have seen that the Pauli vector operator is just rotated in time, and so the block vector has also been rotated in time such that the dot product of the two remains the same, which just means that they are rotated in the same way, which of course is clear because the block vector is the expectation value of the sigma vector. And so if one of them is rotated, then the other one is rotated too. So you have two vectors which are rotated in the same way, and the dot product between the two vectors then stays the same. So yes, there is no time dependence in the row as a whole. However, there is a parametric time dependence in S, and there is a dynamic time dependence in sigma, which are such that they just compensate for each other completely, leaving no total time dependence for the statistical operator. In summary, after solving the Heisenberg equations of motion obeyed by the qubit variables, we observed that the Hamilton operator has no dynamic or time dependence, and the statistical operator has no total time dependence. In the next lecture, we expand this from the qubit situation to the generic situation.